So the evidence for the Big Bang actually came from unlikely places. The reason is that if you look actually very far away, that you can still see the Big Bang. And that's how we found the evidence for it. And these are the first people who managed to see the Big Bang itself. Mr. Penzias and Wilson were working at the AT&T Bell Laboratories, and they were actually studying the new way of communication using radio waves. They built this big antenna for communication with a wavelength of radio called microwave. But they kept getting this strange noise, and they were very annoyed by it. And initially they thought, well, they were working in New Jersey. They thought the noise might be coming from the nearby city of New York. But if you turn the antenna away from New York, they still got the same noise. So that's probably not a human origin. The other way that you may keep getting the same noise, no matter which direction you point the antenna to, is that antenna itself has a problem, right? So they actually got into this antenna and find that many pigeons actually dropping their poops inside the antenna. So they thought, this must be the reason. So they clean it up. They observe it again, same noise. It's not due to the antenna. It's not due to the human activities of big cities. They point the antenna upwards. They still got the same noise. And then they realized that this noise must be coming from the universe itself. It's not human-made. It's not due to antenna. It's coming from everywhere by the same amount. So it's the universe that's giving out this noise in radio. And that actually turned out to be the first observation of the Big Bang. So if you can look 13.7 billion light years away, you're observing the universe the way it was 13.7 billion years ago, when the universe was still hot. And hot universe let a lot of light out. And that light got stretched so much that eventually became the radio wave. And that's what they have detected. And of course, they got a Nobel Prize for this. And the observation has gotten much better in later years. For example, this is using a satellite called COBE, and that studied this radio wave came out from the hot universe, the Big Bang itself. And that radio wave is called cosmic microwave background, or CMB for short. So if you use this satellite and look at every direction you can imagine inside the universe, you get exactly the same amount of radio wave. And so that's this picture here. So no matter where you look, universe is still lit with the light that came from the Big Bang itself. And you also know that this was emitted from something that was hot. Any object that has a temperature will let out the light, where the strength of the light versus the wavelength has this very much fixed shape. And this is called Planck radiation law. And it doesn't matter if you know this law of physics or not. You just remember that anything that has a temperature has a same shape in terms of the color. And that's all you need to know here. For example, if you look at the sun, and this looks like a complicated plot, but the same shape in this dotted red line here. So that's the shape of the color that should come out from any object with a temperature. What's shown in this blue line is the actual measurement, which looks only a little bit different from what you would expect because of some light gets absorbed on the way from the sun's surface to us. So ideal shape is pretty much kept for any object with a temperature. So that's how we know that there was temperature at the beginning of the universe, namely the hot Big Bang. So this satellite called COBE was actually led by these two people, George Smoot from Berkeley and John Mather from NASA. And they got a Nobel Prize for this too, because they managed to map out this shape of the color of the light coming from Big Bang and really verify that the universe really had a temperature. It was hot back then. And the age of the universe is 13.7 or 30.8 billion years. And so they actually managed to look that far away and could see the Big Bang itself. Now, if you look at this picture, you see the temperature is not exactly the same. There's a tiny variation in it. And we'll come back to this question later on. But at the very beginning of the universe, there was already a tiny wrinkles in the temperature of the universe, which actually turns out to be very important in our third and fourth lecture. But anyway, so they got Nobel Prize for this measurement. And when George received a phone call from Nobel Foundation, it was like 2 o'clock in the morning. He got awoke by this phone call, and he was mad at it at the beginning because he got woken up by this phone call. But then he realized that if he was getting a Nobel Prize, he became happy. And what he did was, well, what can I think to do now that I'm getting a Nobel Prize? There's only one privilege you can get on Berkeley University campus, namely that there's a parking spot for Nobel laureates on the campus. He immediately parked his car on one of these parking spots that day, and he got a parking ticket. He had to pay the penalty because technically he still hasn't received the prize yet. He just had a phone call. Anyway, so based on this observation, we now know that the universe was indeed hot. It had a temperature that let so much light out, which now we still observe in the form of microwave radio waves. You also see this tiny variation in temperatures. Later on, another satellite was launched by NASA from the United States called WMAP that improved the resolution of this map. And further on, they actually got improved very recently. Now, there was a little joke about this, that when people look very closely at this part of this map, it seems to show the initial of Stephen Hawking. So somehow, the initial of Stephen Hawking is inscribed in the picture of the universe. Of course, that was just a joke. When the new data came out this year in March by another satellite experiment called Planck, launched by European Space Agency, you can see that this has pretty much faded away. So it was just a little accident. But this way, we kept improving the resolution of the map of the universe, so we really see the universe as it was 13.8 billion years ago. But now comes sort of a sad news about this. Can we just keep looking farther and farther away that we can see the very beginning of the universe some way? The answer turns out to be, unfortunately, no. This picture we see in this microwave, cosmic microwave background, is the wall. We cannot see beyond this wall. And the reason is that when you look back this far away, where the universe is already very hot, the way the universe was is like the inside the sun. If you look at the sun, what you see is the surface. But inside the sun, it's so hot, and the light can't penetrate into it because it's so dense as well. So you can never look into the sun, no matter what kind of telescope you use. In the same way, if you look that far away, 13.8 billion light years away, where the universe was so hot and dense, you cannot see through it because light doesn't penetrate into it. Light gets bounced around, you cannot see through it. So this is the limit, how far we can see with any telescopes. So this actually gives us the following picture. So we live like 13.8 billion years after the Big Bang. We live in these galaxies and stars. If you just keep looking farther and farther away, you look farther and farther into the past. But now comes the point when the universe was like 380,000 years old. Compared to the age of the universe today, this universe is like a little baby just born. But at this point, the universe gets so hot and dense that the entire universe is a soup of electrons and atomic nuclei. There are no atoms even. It's a soup of these particles out there in a very hot, dense form. Light cannot get through it, gets bounced around by many electrons inside this soup, so you cannot see through it. So we cannot directly see the very beginning of the Big Bang itself this way, but all we see is this wall that separates us from this soup of electrons and nuclei and the transparent space after they combine into neutral hydrogen atoms. So this way, we have learned this much so far. We want to understand where we came from, and that's the Big Bang. We're thinking about it 13.8 billion years later. We kept looking farther and farther away, which means farther and farther back into the past, and now we reach this wall. This wall is 380,000 years old universe. It's a baby universe. It's amazing we can still see it. But that's how far we can go, and that's the measurement of this cosmic microwave background. So the question to you then is, can you imagine some other way how we can study the universe beyond this wall, how universe was like? Think about it, and we'll come back to this question.